functions. So I listed 7 types of functions here, that basic functions in mathematics. The first family is called the polynomial functions. Poly means many, nomial means terms. Polynomial means many terms. So the standard form looks like this. F of x is a function in terms of x, which means the function value is determined by the value of x. So here we see an, a with a full node n, a with a full node n minus 1, a with a full node n minus 2, so on and so forth. A with a full node 4, a with a full node 3, a with a full node 2, a with full node 1, then a naught. So all those a's are just some numbers. They are not variables. The only variable here is x. So we see x raised by n's power, x raised by n minus 1, x raised by n minus 2, x raised by 4, x raised by 3, x squared, x means x raised by 1, then constant term. Constant term, this is a with a full node 0. It's read as a naught, N-A-G-U-H-T. So this is called a polynomial function of degree n, because the highest power is n. N is a positive integer. So the first term, so this is the first term. The first term is called the leading term. It's called leading term. And a with a full node n is called the leading coefficient. Okay, so let me write down here. N is a counting number or positive integer, right? So I'm gonna make it a little small, doesn't take too much space. Is a counting number or positive integer. So this term is important for the leading term. And the coefficient of xn is important, called the leading coefficient. Okay, let's see some examples of polynomial functions. The first one is called a constant function. Let's compare with this standard form. So all these a1, a2, up to an are 0, right? Are 0, only a naught. So in this case, -9 is this a naught, is this constant. So so the degree of this is 0. So also this is called degree 0 polynomial. Degree 0. And this one we see x raised by 1. 1, x raised by 1. We don't bother to write 1, just x minus 9. So this we call linear function. Okay, linear function. If we see this kind of function, we only see x raised by first power. And this is a polynomial of degree 1. So on and so forth. We see quadratic polynomial of 2. We see cubic quadratic polynomial 3, degree 3. Quartic polynomial degree 4. Quintic polynomial degree 5, so on and so forth. Well, this one with the leading term is negative x raised by 100. So 100 is the highest power. So this is a polynomial degree 100. So this keeps going on. Let's see some graphs. So constant graph looks like this. So this is f of x equals to a value. So this is a constant function. Constant function is a horizontal line. The linear function could be a line go through the first quadrant and third quadrant, or the second quadrant and the fourth quadrant. Vertical lines wouldn't be a function. Quadratic function, either upward parabola or downward parabola. That depends on the leading coefficient. For linear function, it's the same. The leading coefficient of x is positive, so the line goes from the first and end at the third. If the coefficient of x is negative, the line goes through the second and end at the fourth. For quadratic function, upward parabola means the leading coefficient is positive. Downward parabola, leading coefficient is negative. Cubic looks like this, wiggles. So quadratic is a polynomial degree 2. The graph wiggles once. Cubic function degree 3, polynomial degree 3, it wiggles twice. We see this is wiggles once, wiggles twice. Then polynomial degree 4 wiggles 3 times at the most. It doesn't have to wiggle, but at the most it wiggles 3 times. So on and so forth. So for degree polynomial n, it wiggles at the most and -1 times. So you can imagine this like one piece of string, right? One piece of string. So here straight, wiggle once, wiggle twice, all right? So when we talk about function, we talk about domain. We talk about what kind of value of x works for the function. That's called a domain. For polynomial function family, it's very nice. All real numbers works for it. You see the arrows? The arrow keeps going to the left. The arrows keep going to the right. Right? The arrow keep going to the left. The arrow keep going to the right. So the domain of polynomial function is all real numbers. So we indicate it with a interval notation like this. Goes from -infinity up to +infinity. The second type would be exponential functions. So the standard form is a multiplied by b raised by x. B here is a base, right? B is a base. And x, the variable x, a also is some number. A is some number, b is some number, and x, x is a variable, right? Function in terms of x is a variable. So x appears in the exponent. So that's why it gets named exponential functions. So we have a condition. We want to be positive. Be positive. All right. Be a positive number. Because imagine if b is 0, like 0 raised by any number would be 0. The whole thing would be 0. If b, and also we don't want to deal b equals 1. We don't want to deal with b equals 1. So we want to be not equal to 1. We want to be not equal to 1. Oops. Because if b is 1 raised by any exponent would be 1. Right? It's not interesting. So this whole thing will be 8. That tends to be a constant function. So I have those two limitations. A has to be a positive number. then a b has to be a positive number, then b not equal to 1. Let's see the graph. So if b is greater than 1, right, we have a graph like this, right? The graph like this. It goes upward. In function, we call this increasing function. If b is positive but less than 1, we have this kind of graph. So it goes down. We call this kind of function decreasing function. So this is called exponential growth. This is called exponential decay. Exponential growth, we can talk about human populations, right? Either it grow or it decay. Now, in a couple of countries, the population is decreasing. Domain of exponential functions similar to polynomial functions, all real numbers. Okay, works for all real numbers. The third type is logarithmic functions. The function looks like this. Log with a base with a value of x, and x appears in the value. Log base a of x. And the graph looks like this. So when the base a is greater than 1, we have this increasing function, the blue color. When a is a fraction less than 1 but positive, we have this decreasing function, the green graph. So what's the domain of this function? The domain function takes positive values. Positive values. So x here has to be positive. So this x has to be positive. I should write here. X has to be positive. So that's the third kind. The fourth kind is in a radical form. Radical form. We see this one, square root of x. Right? The graph looks like this. It's starting from 0, then gradually goes up, square root of x. And domain goes from 0 to infinity, including 0, right? Because square root of 0 is just 0. So this start with 0. Comparing to log functions doesn't go from 0. It starts from value bigger than 0. Okay, so that's why this is a parenthesis, it's not a bracket. So see, this one is a bracket, means the domain has 0 in it. Cubic root function. So we see this is a index is 3. So cubic root of x. The graph looks like this. And this one, so the index can be any number. 3 can be 4, can be 5. So in general can be nth. So this is nth root functions. Nth root of x. So the fifth type is absolute value functions. So it looks like this, absolute value of x. So x can be any number. That's why the domain is all real numbers. Graph looks like this. Graph looks like a V shape. It could be upside V or downside V. Right? Rational functions, the basic form. You look at this, it's basic form, it's not a standard form. Okay, this is basic form, standard form, because it could be more complicated in this. But as long as it involves absolute value sign, same here. As long as the variable x appears in the denominator, so that function is called a rational function. X appears in the denominator. So this is a graph of 1 over x. You see it has 2 branches or 2 pieces of strings. One in the first quadrant, one in the second quadrant, one in the third quadrant. And of course, what is the domain of this one? We see 1 divided by 0 is not defined in math, so x cannot be 0. As long as x is not 0, it's fine. Any other values work for this function. Only 0 not working for this function. So writing in interval notation, we read like this. Goes from -infinity to 0, then union 0 to infinity. You see here, not including 0. This one not including 0. So 0 is omitted from this notation. A more complicated example of rational functions like this. The numerator is x plus 2. The denominator is 2x squared minus x minus 3. So how do we find the domain of this function? We take the denominator, we set not equal to 0. Okay, the denominator in this case is 2x squared minus x minus 3. We said that cannot be 0. Then we try to solve it. So solve, factor into a factor form. Then 2 factors, multiply to be 0. That means each one can be 0. That's a 0 property. Or 2x minus 3, not 0. That means x cannot be 3 over 2. X plus 1 is not 0. That means x cannot be -1. Okay. So as long as x is not 3 over 2 or -1, the x value works for this function. So this function just doesn't work with the 3 over 2, doesn't work with -1. So using interval notation, we represent it like this. X value can go from -infinity up to -1, then from -1 up to 3 over 2, then from 3 over 2 up to infinity. So the sign in between is called a union. The graph looks like this. We have 3 pieces. All right. So rational function is a little bit difficult than polynomial functions, right? And the graph is not one piece of string. It could be 2 pieces of string. We see this one. We have 1 piece. We have a second piece. And this one, we even have 3 pieces. So that's why rational functions is a little more work to understand. So note, domain for rational functions is not unified as polynomial or exponential or absolute value function or square root or cubic root, right? So it's case by case. It depends on the denominator of a specific rational function. So what do? We just take the denominator, we say not to be 0. Okay, so maybe we can make this. We make this. So domain is the denominator not equal to 0. All right. So whatever the denominator is, we set the denominator not to be 0. Then we solve for the x value. So then the last type is trigonometry functions. So usually we just call trig functions because it's too long. Logarithmic functions, we just call log functions, right? So trig functions has 6 types. So sine x, cosine x, and a tangent x. And the inverse, multiplicative inverse. So cosecant x equals 1 over sine, or secant x equals 1 over cosine, or tangent x equals 1 over tangent x. So there's 6 kinds, and the graph looks like this. So sine is this wave, cosine is this wave. They look very similar. So those graphs actually is the same, but only shifting by 90 degrees. So as I'm talking right now, I'm making sine cosine functions because my sound making these sound waves. So this is tangent x graph, right? This is cosecant. Cosecant equals 1 over sine. So you see the graph is different, is almost like opposite, right? You see, sine has no graph under this, but this cosecant has this piece graph. And then no graph above this, and cosecant has this. So if we do this, if we trace out this, that's exactly sine function, right? So secant, same thing. Secant is 1 over cosine. So the graph is related with cosine. Cotangent is 1 over tangent. You see, also it's a flip of the graph. So those are basic 7 types of functions.